So a few words about myself. I'm a mechanical engineer. I have a master and PhD from the National Technical University of Athens. And I have been working in uh, intelligent process monitoring and control for composite manufacturing more than 20 years now. So a few words about Synthesites. Uh, we are a company based in Greece, Belgium, and the UK. We have been working a lot, as you can see from our customers list, with aerospace companies uh, practically around the world. We have customers in Europe, US, Australia, recently in South Korea. And we are also working, we are very active also in wind energy for um, process for process monitoring of the manufacturing of wind turbine blades. And we are also, of course, we are working with R&D centers and university, mainly in Europe, with the leading relevant research centers in Europe, but also in Australia and in the US. So why we need process monitoring? Because as you may know, the state of the art in composite, in monitoring of composites in manufacturing is mainly pressure and temperature. Why we need something more? For sure, we need it because we need to check what's happening in the mold, and with temperature and pressure, we can we don't know exactly what's happening in the mold during manufacturing. So with some intelligent sensors, you can check resin quality and adjust the process accordingly. Detect accurately resin arrival at critical locations and open and close valves in case you are doing some process control. Monitor viscosity changes of the resin, of course, and decide when start heating and injection. Identify minimum viscosity and decide about pressure. This is mainly about autoclaves and prepregs. Detect unexpected events, of course, and follow alternative roads. Improve simulation accuracy and design intelligent strategies. So sensing and simulation it's complementary, and both can use either to improve the accuracy and the information that the user can get. And of course, real-time decision about the cure cycle based on TG and degree of cure rather than time. In our case, our role in Morpho was only about process monitoring of the RTM process. So we have introduced the optimal system, which is mainly for viscosity and resin cure. The OptiFlow system, which is about optimizing, monitoring the mold, the resin flow, and optimizing the flow. We have also our own durable and disposable sensors, and we have our own software for data acquisition and for providing online the degree of cure, TG, and viscosity. And we have also automation solutions that are used complementary to the sensors and the monitoring in order to improve the inside of the process. About Optimold is let's say a kind of dielectric system, but is used DC excitation in contrast to AC, which is used by the conventional dielectric systems can measure electrical resistance up to 100 teraohm, and at the same time, it measures also very accurately the temperature at the sensor. There are various sensors, durable sensors that can be mounted on the mold, or disposable sensors that they can embed it in the part. And we have recently developed some new durable sensors, mainly for aerospace, carbon fiber manufacturing, and wind energy. Similarly, there is the OptiFlow system, which is again based on DC excitation, but it can measure up to when the resin is liquid. There are again durable and disposable sensors that can be installed in the mold or embedded in the part in order to check the resin arrival and temperature. Within Morpho, we have extended, let's say, the CF Q sensor design. The CF Q sensor had been developed in order to measure the to measure in case there is a carbon fiber in presence, because as you may know, with dielectric sensors, the problem with the carbon fiber is the carbon fiber just short circuit the electrical field, and the sensor cannot measure. So we had developed this CFQ sensor before Morpho, but within Morpho we extended the concept in order to have also resin arrival sensors for carbon fiber parts, which is very relevant for aerospace manufacturing. Furthermore, we extended also the concept of the Cure simulator for RTM applications. So in this case, in the previous European project, we developed the Cure simulator to measure the curing in the autoclave in a part, and within Morpho, we extended this concept in order to use it for RTM parts. So in this way, we don't actually need any cure sensors in the mold, but we can, let's say, emulate the curing outside of the mold using the temperature of the mold and the resin of the mold. Just to get an idea of what you can measure with OptiMold, you see a typical RTM6 cure cycle, temperature and resistance. Initially, when the resin arrives, the resistance from air, from very high, it goes very fast at around 10 megohm. Then the viscosity increases during the first part of the injection. The minimum viscosity, gelation after the heating ramp, and the end of cure and the cooling. Furthermore, what we want to do within Morpho was to use the raw data, resistance and temperature, in order to provide in real time, through calibration, viscosity and TG, with the target to control in real time the manufacturing process. So we ran some tests in our lab to see how the measurements from the OptiMold and the Cure sensor correlates to viscosity. At first, you can see that there is a very good correlation between resistance and viscosity at two injection temperatures, 160 and 165. Which was a very promising result. We have also run tests to measure the TG with DMA coupons in this case, and you can see on the right there's a very good correlation between our estimation and what was measured by Safran. So on your left, you can see the preform, the carbon fiber preform, the RTM mold, the closed RTM mold before the press is closed, and on your right, you see the final product. We have installed several monitoring systems on the back of the press, together with a Q simulator. So we had 4 OptiFlow and 5 Optimal systems, and we have installed also several sensors in the mold, 15 resin arrival sensors, and 3 cure sensors, as you can see here, and an inline sensor. You can see also some pictures of the sensors installed on your left, and the cure and resin arrival sensors and the inline sensor. Just to have an idea of the measurements, you see the temperature and resistance in one graph together with the online TG. And on the graph at the bottom, you can see the resin arrival times. This is something, the information you can get in real time, which is very important for the operator, for example. We run, I think we ran about 11 injections in total throughout Morpho project, just to have an idea of the different flow patterns, because in the beginning we used also the optical fibers, created some issues with the flow. So you can see how the flow was affected in one of the cases. Also, we used a narrow preform, so that means that there was much higher race tracking, and all these issues were picked up by the sensors. You can see some of the flow patterns here. These were from the first injections where there were some issues, and then as the technology and the optical fibers installation improved, you can see that there was a more conventional, more much better quality of the flow patterns. For the process optimization, we have seen that we could shorten the injection time, and also based on the online TG, we could also shorten the curing phase in order to, let's say, shorten the cure cycle, the production cycle in total. We have thought about different cycles to do this, to optimize the time. And finally, we selected, Safran selected to run, let's say, a single injection and curing cycle. That means that the injection and curing happen altogether at 190 instead of injecting at 160 and then ramping up to 190 for the curing, which is the original cure cycle. As you can see here, these are the comparison between the 10th and the 11th injection, where you can see that without the ramp, so injecting at 190, we could save a lot of time. I think around 50 minutes, comparing to the two temperatures cycle. So in conclusion, the new CF resin arrival sensors have been applied successfully. I could say that we have achieved over 98% robustness, and this was just the first, let's say, stage, first development stage of the sensors. The use of the new CFQ sensors and calibration methods can lead to significant reduction of cycle time. The introduction of the Q simulator can considerably facilitate the implementation of this technology in everyday production, and this is something that we have already implemented in wind turbine blade production, and its implementation in our space is ongoing. Thank you very much.